So today I would like to talk about Hilbert modular varieties. But before I do that, I would like to make some remarks and comments about the Heck symmetry on the tower of modular varieties and also on the Heck correspondences, because we are going to use some of these properties, and I think it may be good to write down some definition so that people can see how they come from. And this was also related to questions some people asked. So remarks on Heck symmetry. Before giving the algebraic definition, let's start with a case that everybody is familiar with, especially given what happened in the previous weeks. So illustrated in the case of modular curve. Okay. So I take the upper half plane, which I denote by H, and then we have the well, everybody has seen them. If I take an n, think about the principal congruence of group of level n, and this, I guess this is usually denoted by y of n. And as n varies, we get a tower of modular curve. Okay? And we like to see, so we have, let's say, so we think about the system of y of n's, and this in our notation will be sort of A1, maybe A11. This is the modular curve. And the claim is that on here, also on any level, any quotient, the group of automorphisms is pretty small. This is an affine curve, generally of high genus. There's not going to be a lot of automorphisms. But if we pass to the whole tower, then I claim that we have a very nice action. Okay? What's the action? Let me just illustrate how SL2Q will operate. Okay? But the actual group of symmetry is a lot more, because when you have SL2Q operates, then you can have the completion of it operating on it. This is so completion because of this. You have a projective family, then you can have certain kind of topology. I'm not going to write down the details, but let's just look at the action of SL2Q, because this is most easily seen in classical terms. Okay. Sorry. This is essentially the adelic completion. This is completion in SL2 of finite adels over Q. And in fact, so this is actually equal. So this is equal. So actually equal to SL2 by strong approximation. Okay, so how does one do it? So if I take given gamma, so let's say it's an element of SL2Q. Now I'll say I would like to get something operating on this. So, but we have a tower, so by definition, a projective system, we're going to get a map from the projective system to itself. So it suffices to show, so if I can have a high enough n, then I can get a map from y capital N to y lower n. And then doing it in a compatible way, that will give me a map from this projective system, A11. So this is the projection. And then this is not the projection map. So this is a map induced by gamma. And so composition, I get a map given by gamma. And we do it for every gamma, so we get an action. So now what do we do? So we'll choose. So I fix in small n, and I choose a capital N such that, I guess, let me try. Gamma of n, capital N, gamma inverse is contained in gamma of n. So this if you choose capital N large enough, this exists. Exercise existence of such N, such capital N. Okay. Now, then you say, I guess this is pretty easy if I did it right. So if I take an element of Z, let's say tall in H, then we'll think about, let's say U, so take an element UN in capital gamma of capital small n, capital N. And I would like to check that if I hit tall with gamma and comparing it with hit UN of gamma, UN of tall with gamma, and they land up at the same point in y sub little, what parenthesis little n. Okay. Now this should be clear. So we'll check. So this times tall is gamma times U sub n, gamma inverse times gamma inverse, gamma tall. So, but this is in gamma of n by our choice, and therefore we got the required step. Okay. So, okay. So we have seen that we have such actions. Okay. Now, the next thing I would like to say is that we can do a similar construction algebraically. Do or define. Okay. Now, as you can imagine, there are many ways. They all turn out to be equivalent. So I guess we have to just choose one way. So okay. So I guess the easiest way to see it is to do it in an adelic way. So do this for AG1 tilde, which is the projected system of AG1n's. And I remind you that n is bigger than or equal to 3, as always, and n is supposed to be prime to p. So this is GCD of these two are equal to 1, because we only look at the prime to p tower. Since we will be working in characteristic P, therefore it's not a good idea to have a level structure at P. That creates lots of problems. Now, so I guess the real thing is that I need to explain what's a point here in this tower. So description or definition of, let's first recall description of points of a G1n for fixed n. That we remember. So a point of G1n corresponds to, so the way you typically get a point is that you have a G-dimensional principally polarized abelian variety. I'm not sure which, okay. I have a principal polarization. And I have eta. Eta is a level n structure. So here, let's say, so eta 0, what's a level n structure? I think the best way to think about it is not to use Z mod nz, but n inverse Z mod Z, 2G copies, and together with the standard symplectic pairing, and we want to rigidify the n torsion points together with the pairing on the n torsion points coming from the principal polarization lambdas. Okay. So this is one. Now, so suppose we have such. So this is what happened at one level. Now, if we have a point in the projected system, what do we have? We have one such point for every level, and these levels are compatible. So we see that a point in AG1 tilde. What's a typical point? A typical point is represented as follows: A lambda as before. So I guess there's a 0 here. And now eta is somehow different. It's a compatible system of things. Now, what's a compatible system of this? One way of writing it is that I take AF. So this is the finite prime to p adels, whose definition I wrote down before. This is the restricted product of all QLs, L running through all prime numbers different from P. Okay. And this is the formal completion of, the profinite completion of Z without P part. So this, if you like, so this, another definition is that this is just a product of all ZLs, L different from P. So so what is this? This is, if you like, this is QL mod ZL, and then direct sum of taking over all L different from P and 2G copies. Oh, there's no 2G, but I'm going to write 2G copies. So that's that. And then and then on here I can have a standard symplectic pairing. And here I mark it with a 0. And now I write prime to P. So all prime to P torsion points. And on prime to P torsion points, we have but the symplectic pairing then takes values in one copy of this. Just like, sorry, if you fix in level n, so you have n inverse z mod z, 2G copies, and then n inverse z, z 2G copies. And now you can depend, I guess, or let it land in n inverse z over, and then take the limit. Sorry? Okay. So we have this, and now, so I guess the easiest way to see this action is as follows. We have, suppose we give ourselves a marking which was written that way. I'll ignore the polarization part in writing. So I have a 0, so no p, prime to p. Now the way one sees that is one first go not to here because it's not easy to have a group operating on it. Now, so I have a gamma. So I have a gamma precomposing it with AF P2G. So now what do we have? We have this map over here, and then we would still like to trace it over here to G. And now here's a problem. There's a little problem. The problem is that I don't know what to fill in. Here is, they are contained in this abelian variety. Okay? Now, the standard way, if you think a little bit, is that what we are doing is making an isogeny. So I'll fill in with an abelian variety B here, so that here this arrow is not a morphism between abelian varieties, but rather this is a prime to P polar, it's a prime to P quasi-isogeny. Meaning that it's the composition of an isogeny whose kernel is prime to P, and then composed formally with the inverse of another prime to P isogeny. And now here, and you can convince yourself that there is a unique B, well-defined, that is making this diagram commute. And that is the definition of the action. So the action of gamma produces this. And this is a polarization. Oh, sorry, this is a level, infinite level structure. I call it infinite level structure. So this is the definition. And you can check that this, so if you interpret, so for instance, in the modular curve case, you can see it's a good exercise to see that it coincides with the previous description. Okay. Now, why did I do this? There is a reason, and the reason is, I guess you have seen in France's lecture, I think the first lecture, an explicit definition of Hecker orbits. Okay? So the exercise is to check that using this definition of the tower, you will recover the explicit description of a prime to P Hecker orbit as in France's talk. So recover, check, description of, in France's talk, this is denoted by H upper P as P times x0 if x0 is this point. Okay. Sorry? Here it's not just, you see the group is this. This is it's the finite adelic group operating. But of course, because of strong approximation, you only have to know how the rational elements act. They are the same. Now I will, before starting the Hilbert modular varieties proper, I would like to state 1, so lemma, in fact. But to make it easy to remember and to induce you of thinking it to have some importance, I'll give it a name, and this, I guess, or what I usually call it is local stabilizer principle. So if you like, this is a lemma with this as its name. What it says is the following. Suppose I have a closed subscheme of AG, 1n. Let's say that it doesn't matter, but for simplicity, let's assume that it's reduced, if that makes one feels better. That's not important. Now, so I would like, and I will make one assumption. So assume that Z is stable under all prime to P Hecker correspondence. And we'd like to draw some conclusion out of this assumption. Okay? And the kind of assumption one would like to draw is a local one. So I have a point Z0 in it. I'm assuming that it's a closed point. And this, let's say I'm working over at P bar for simplicity. And the local assumption, the local conclusion I would like to draw is the following. So so here is a little definition that here, given the situation, I think about what I call the unitary group attached to a 0 P infinity and star lambda 0. Okay. So what is this? So this is, I'm sorry, it's not 0. Cancel this. So what it is that I'm just looking at all elements X, which has this form. Essentially, they're prime to P quasi-isogenies. So this here, this tensor product is the set of all prime to P quasi-isogenies. Okay? And I want to look at those which has the property that if I apply the Rosati involution to it and multiply it with itself, I just get identity. So this is a standard unitary group construction. These are the quasi-isogenies which are compatible with the polarization. There's nothing else but that. Okay. And if you follow this definition, I'll leave it to you as an exercise. That this is exercise. That this is the, again, quote unquote, the stabilizer subgroup of X0 inside Hecker correspondence, Hecker symmetries. Maybe I have it. So I'm not going to prove it, but this is an exercise. Why is this an exercise? If you look at this diagram, which is still here. Now, generally, it's hard. In general, this B0 is not A0. It's just not that. Now, but if gamma is a prime to P quasi-isogeny that preserve the principal polarization, then B0 can be taken just to be A0. That's clear. Because gamma, so this element gamma sort of maps to itself, and so you make sort of in a tautological way this diagram commutes. And the local stabilizer principle, the lemma, it says that then Z localized or completed as Z0. So I remind you what this is. This is a formal subscheme of this smooth formal scheme, which is the formal spectrum of power series ring. Okay. So the conclusion is that this is stable under the action of U, I'll give it a name, H sub x0, or H sub z0. Why does this make any sense? It's clear from this construction that this is contained in the automorphism group of A0, lambda 0, passing to its p-divisible group, just by its very definition. Therefore, and you remember that when we described the deformation theory, formally, just from the definition itself, there is a natural action of this group operating on the deformation space, and that's the deformation space. And this is the statement. That's the end of the statement. I have some comments. So this looks, I don't know how anyone feels, I mean, either too trivial or too abstract. But what I would like to say is, first, this is almost a tautology. So to impress you that this is a tautology, I'll declare that this is a doable exercise that you can really do just by following the definitions. Okay. Now, second is that I'll say that, in fact, although in this form you don't recognize it, but in some other form, you have seen it, so I don't know how, a long time ago, and used that, you have taken it for granted. What's the analogy about this statement let's say, in differential geometry? In differential geometry, let's suppose, so let me put a small box here, suppose have M is a manifold. You have a Lie group operating on it, here, and then you have a submanifold X contained in here, which is stable under G. Stable under G. That's okay. Now, then you like to sort of draw some conclusion from about this in local way as a differential geometry. Okay. So what would you do? You take a point X of that. Now, X is not necessarily fixed by the whole group G. Okay. But you can look at the stabilizer subgroup of Gx. So it certainly sends Gx to itself. And then, so in differential geometry, you say that, well, so this sends the tangent space of X to itself. But you can say more, that it sends the jet space to itself. The local jet space, the jet space of X as a subspace of the jet space of X at X, of M at X. Okay. So I'm sure that this is easy. And what's this statement? It's exactly the algebraic analog of the previous one, except one slight difference, that we don't have a genuine group action on the modular space, but rather we have something which sort of like a group, and it came from a group in the tower, but after you look at just one fixed level, and you don't see the whole group action, you only see the remnants of the group action. But that still allows you to draw this conclusion. Okay, that's that. I've spent a long time on this. Sorry? What's the jet space? The jet space is, I don't know. Maybe I should talk to you later.
Formal completion.
Algebraically, it's the formal completion. But that doesn't make you happy. I'll talk to you later. Okay. Now, but I would like to make one more remark before quitting. That is, this looks very stupid. But why is anyone interested in it? The true reason is that if in these contexts, so if I have a subvariety stable under the Hecker symmetry, and we'd like to draw any conclusion from it, any conclusion about that assumption, to get any information of Z, I don't know any other way other than this stupid principle. I don't know how to get started. Okay. And if any one of you has any way of getting started, I would love to know. But so far, that's the only way that I know. Okay. So how to use it? So we'll come back to that later. So how to use this? Well, so it's obvious that if you want attempt to use it, you need to get some point whose local stabilizer subgroup denoted by H sub x0 there is not trivial. If it is a trivial group, you have absolutely no information whatsoever, right? So to say that, to get to the point that there is some non-trivial local stabilizer subgroup, we need at least to have some abelian variety whose endomorphism range is not too small. Okay, now we have all seen that there's a source of ample supply for such points. What are they? Abelian varieties over finite fields. So apply to x0 over z over p bar. Then the abelian variety over finite field had sufficiently many complex multiplications. They have lots of endomorphisms, so that group is guaranteed to be sizable. It may not be certainly not as big as the whole symplectic group, but it's not trivial. So that's to apply this to, that's one. And then we need some way of getting information about formal subschemes stable under such actions. Now, in general, again, this is problematic. I think it's a useful, important for me, maybe not for any other people, but it's some hard question. It's some question that I would love to be able to solve in general. I can't. But in one situation, so far that we've discussed, there is one situation we can get a lot of information. And this is something I mentioned, I think, at the 2 days ago. And this is something I labeled as local rigidity. I remind you orally what that says. It says that if you have a formal torus, and if you have a subgroup of automorphism of these formal torus, and operating in somehow not totally trivial way, then, and you have some formal subscheme, irreducible, reduced, which is stable under this action of this subgroup, then you can draw a conclusion that that subscheme is a formal subtorus. And that's a whole lot of information. And this is something we're going to use, probably not today, but on Friday. Now I've used half of the time without touching the main topic I'm supposed to do, which is Hilbert modular varieties. So we'll So Hilbert modular varieties. I'll first give the definition. And the definition itself, if we want to make the correct one, somehow it's not easy. It's not the obvious one. So, Hilbert modular varieties. So, in general, because of data purpose, I need to take a product. So, the Fi is totally real. So these are in the notes. And then I'll take L is an invertible OE module. And L plus is a notion of positivity. And this makes some sense. Well, it makes sense because of the totally real assumption. And then n is bigger than or equal to 3, prime to p. And now, so Hilbert modular variety, that's denoted by the input data. So it's indexed by the input data. What it does is that for every scheme, for us, since we are going to work over FP bar, why don't I say it's over FP bar? Then it's attached, it's very much like the case of the Ziegel modular varieties AG1N. So this is a abelian scheme. And there's one condition on the dimension is equal to the dimension of the product of totally real fields E. And then there is another piece of information, which is that this abelian variety admits multiplication by the ring of integers of E. Okay. And then I have a polarization. Now, this polarization will look a little strange, but it's essentially the same as what we had before. But instead of pinning down one polarization, we will define a lot of them. So in fact, what that is that it's a homomorphism from this invertible OE module to the symmetric homomorphisms of from A to the transpose of A. That's the dual abelian scheme. And we want it to be OE linear. I remind you, OE means the following. Symmetric means the following. If you have a homomorphism from A to its dual, then taking the dual, you get another homomorphism from A to its dual. To say that it's symmetric means that that's the same. You get back the original one. Okay? And you want such a map, which this map, again, is OE linear. And you want that L intersect sort of positive elements that got mapped to polarizations in the previous. That is, sort of locally in the flat topology, it's induced by ample invertible shapes. Okay. Sorry? Oh, positive. This is a notion of positivity. So it's just that you take L tensor with R, and then you want is irreducible. Let's say you want. So this is not connected. Sorry? Oh, so what am I saying? Yes. So L. What am I saying? Let me say this. So L tensor R is a product. It's a lot of union of R's. the non-canonical, but as R vector space. And then I choose one component for each of the factors. That's a notion of positivity. Sorry? Yeah. So, what am I saying? I'll take R. Let me just write it this way. There certainly is a more intelligent way of writing it, but it escaped me at the moment. So look at this subset and choose one connected component of it at a time. And that's a notion of positivity. So pinning down, this is in a non-canonical way. So choosing a strict ideal class group. Choosing an element in the strict ideal class group. Okay? So that's that, and then the n is eta. That's a level n structure, and I'm not going to write it down. So it's written down in the notes. So you pin down the effect of points of level n. Okay. But this is not n of it. So that's something one has to be careful about. So if anyone is interested in getting a precise definition, but there's one condition. Maybe I should go this word. The condition, in some sense, says that locally there is a principal polarization sitting inside L, sitting inside all possible polarizations. There's a lot of them, but it's not really an infinite collection of data, because once we have one, we can multiply it with a totally positive element to get another polarization. If we don't want to put a positivity condition, so from every symmetric element, you multiply it by some element of the ring of integers of E, you get another symmetric isomorphism, a symmetric homomorphism. Okay. So this condition that we need is abstractly says that this is an isomorphism. Okay. Now what this means, so is that, it's easy to say what that is abstractly. Abstractly, I'm thinking of A as a sheaf. Now, so in the category of sheaves, I tensor A over OE. So A is a sheaf with actions by OE. I tensor it with L. I get something. And because the way L is defined, there's a natural map. And one requires that this is an isomorphism. So what that means is that locally, over the base, you can find some element of lambda such that lambda induces an isomorphism from A to its dual. That's all it means. But because of this local invertibility, we want to pin it down. That's because if you don't, you get a large number of irreducible components of the modular space. Okay, so that's that. Now this condition is due to Deligne, a paper in Deligne and Pappas. So maybe it's good to tell some history about this. So and authorities in the room can correct me. I'm not certainly not the authority about the history, but as far as I know, the reason that people got seriously interested in the modular schemes in an arithmetic way is because Deligne realized some year, I don't know exactly when, certainly before the early 1970s, Deligne realized that one can construct p-adic L functions over totally real fields. There is a catch that he needs certain irreducibility statements. He needs actually two of them. One is that the modular scheme itself is irreducible. And the other is that so-called Igusa towers, which is, so you look at the ordinary locus, and then you look at all possible trivializations, and still is irreducible. So it needs these two. Now, these two were resolved by two people. The irreducibility problem was resolved by Rappaport in his thesis published in the Compositio. I don't remember the exact, maybe 1976, plus minus 2. It's in the notes. And the irreducibility of the Igusa tower, which is a statement modulo the irreducibility of the moduli space in characteristic P, was resolved by Hilbert. And then, sort of combining these two, so the linear Hilbert wrote a paper about the construction of p-adic L functions, construction of the, and then the interpolation properties, and so on and so forth. There is a catch. The catch was that in the late 1980s, George Pappas, who was a graduate student at Columbia at the time, was trying to do something about modular varieties. And then he was playing with it, and then he realized that there is a problem in Rappaport's definition, which is not this. The problem was that there are certain points that got missed in Rappaport's condition. So Rappaport's condition is, instead of this condition, he requires that the Lie algebra of A over S, which is obviously an OS tensor OE module. Okay. And now, if I take, let's say over a point, let's say even over perfect field or algebraically closed field, that doesn't matter. So then I have K over that. He requires that this is a free this K tensor OE module of rank 1. It's certainly that module, and the size match. Okay. The problem was that it doesn't, if we impose this condition, it misses out certain points so that you can have a family going, the abelian variety doesn't degenerate, but then from some the generic points satisfy this condition, but the special points doesn't. There's no way to fix that. Okay. So in Rappaport's thesis, or what he did was he constructed a good compactification. He compactified it at a boundary toroidally. And then the proof was, or to prove irreducibility, you invoke that, well, the generic fiber is smooth. There's nothing bad happening in characteristic P, and therefore conclude that it's irreducible. But for that, one needs that the closed fiber is proper. But not only proper, so it doesn't have two bad singularities. One needs some condition about being unibranch. Since one's missing some point, the proof developed a hope, a serious hope, because lots of other papers depend on it. And that's sort of about 10 years after that. But then the linear, of course, took him little time figuring out what the right condition was and fixed that. So this is the condition. Now let me tell you a few properties about this. So now this is serious black boxes. Lots of them. Okay. One is that, by the way, I should first remark that N, E, so L plus, but by this very definition, it's just a product. If you have a product of totally real fields, then an invertible sheaf decomposes, and then notion of positivity also decomposes. So generally, this is not a problem. Okay. So that's that. So let's assume, so that's a remark, but it's not, it's not important. So the point is that one is that over Fp, let's say N, E, L plus N over Fp bar in general, it's singular. There are singularities. Okay. But it has local complete intersection. Every point, that's the worst it can happen. 2 is that codimension of singular locus is at least 2. Okay. Now 3 is that it's irreducible. And 4 is something that we are not going to use. And we are not going to use that has sort of singularity has high codimension. We're not going to use it has local complete intersection property. We do need this property later. And so I'll say that M-E-L-L plus N has a stratification by Lie type. So let me tell you briefly what this means. So suppose I have an abelian variety with real multiplication by E satisfying those conditions. So suppose I have A over K and iota, lambda, and eta, etc. Eta is not important. Okay. Now we can look at the first Duran homology of A over K. What can we say about it as a module over let's say K. K has characteristic P, and so OE. What we know is that this is free of rank 2. It's free module of rank 2. And this is something you can do by what you know now. Although I don't claim that this is trivial. It requires a little bit of thinking. But this we know. Now we have, because we have a Hodge filtration. You remember the Hodge filtration we wrote down before. Therefore, if we think about it in the Grothendieck group of modules over this ring, this class is equal to the Lie algebra of A together with the Lie algebra of the dual of A. There is another dual, but dual doesn't change it. So just like that. This comes from the Hodge filtration. Then, but these two are the same because of the condition we require. So there is locally some lambda producing an isomorphism from A to its dual, compatible with the OE action. So the conclusion is that this is equal to the class of K tensor OE in the Grothendieck group. I guess the standard notation is K prime of OE tensor K. So this condition, it's not necessarily free, but if you pass to the Grothendieck group, it's correct. Now, there are some conditions, or there is also, we know that the filtration, if you look at the filtration, it has to be maximal isotropic. That's a property because it locally has a principal polarization. Okay. So using that, we can think about the type of this Lie algebra as not an element in the Grothendieck group because we know what that is, but rather what that actually is by its isomorphism type. There are only a finite number of them because let's assume that K is algebraically closed. Then, by an exercise that all of you can do, this is a special case of the structure theorems for modules over principal ideal domains. That you know that there are only a finite number of isomorphism types of this Lie algebra. And you can stratify the moduli space using the isomorphism type of that Lie algebra. That produces a stratification. One of its the largest stratum is exactly the non-singular stratum. And all the others you can analyze. Okay. Now I have about 5 minutes left, I think. And let me quickly go see which ones are more important. Okay. Here's one thing. So I was planning to say something about how to prove the statement about singularities, but I don't think I have any time. But I think the following may be useful to see. Okay. So first, I would like to state a general principle. So let's, for simplicity, let's say there's just one totally real field. Okay. So now I have an abelian variety A, and have eta and lambda, so as before. I have such a thing, A0. Okay? And we'd like to understand its deformation theory. Okay? Now, and by Serre-Tate theory, we know how to compute its deformation theory. The deformation theory, we know that it's the same as deforming its Bersati-Tate group. Right? Now, the point is this. So if we think about the deformation theory of A0, iota 0, lambda 0, let's forget about iota depolarization for a while. It doesn't really matter. Okay, so let's just think about this for simplicity. Now we know that this is the same as deforming its Bersati-Tate group, iota. Okay. Now the point is that the Bersati-Tate group decomposes into a direct product. Why? Because if I take the Bersati-Tate group, now I have OF. OF, if I tensor it with VP, we know that it decomposes into the product of OF sub P's. P divides F. For every place, so you can look at various places, if there are more than one prime in F above P, for every one, you get a ring of integers, and you have this canonical decomposition. Now, in this decomposition, you have one irreducible idempotent for every place above P. So, in fact, every Bersati-Tate group with endomorphism by OF, so in this situation, so it will decompose into a product by using these idempotents. So, therefore, we have a canonical decomposition of the Bersati-Tate group of the deformation space into the deformation space of the torsion points using powers of various primes above P, precisely because of this decomposition. Okay. Is it clear? Let me say it orally. So the reason is, suppose you have an A over R. R is an Artinian local ring that decomposes. Now we know that, so A infinity, P infinity, so we have A infinity over R. But A infinity over R, again, using this decomposition, it decomposes into the product of A over P infinity over R. Each one is a deformation. So it comes for free. We have this decomposition. That's one. Okay. So at any point, so although you certainly shouldn't expect to have any decomposition of the moduli space itself. It doesn't exist. But locally, it looks like it has a decomposition. Okay. Now, for future purpose, I would like to give another exercise, which is pushing this fact a little further. How do we? So, in other words, I would like to globalize it. how do we make such a statement global? This is a point-by-point statement, right? Now, but if I have, I'll just write m instead, so I'll omit all these indices. Now, the claim is this, that if I move these deformation spaces on the modular space, I'll keep these decomposition. Now, what do I mean by that? Well, Grothendieck taught us that if we want to think about sort of infinitesimal properties, we should just look at sort of, we know that we can embed this M, this modular space, diagonally into its product with itself. And then you formally complete along the diagonal. So that way you get all the what I call jet spaces in an algebraic way. So, and then moves globally. This is a formal scheme. As projection, you can use either of the two projections. Let's say I use the first projection. So this is the family of, so to speak, tangent cones. Okay. And then the statement is that this decomposes into, as a cone, it decomposes into a product. This is a fiber product over M. And I declare that this is an exercise. What does one use? It's nothing but Serre-Tate theorem. And this is how one, so looking at such a statement, actually there's a global meaning. And this we will use next time. And okay, I should stop. Thank you.